We start. What is digital? Actually, we are dealing with digital electronics. What is digital? First, we have to know what is analog then. An analog system, it has continuous range of values. You'll see the graph also just now. But before that, see mercury thermometer. You have seen that thermometer. You see in that thermometer mercury level is there. That corresponds to some analog signal, analog value. Then vinyl records. Of course, your human eye. The eye uses analog technology. It uses analog technology to record what it sees. While when we are discussing digital systems, it has set of discrete values. This is very important. Discrete values, what do we mean when we say discrete values? That I'll just show now. But before I go ahead, this is digital thermometer, CD, digital camera. You have all been using this for a while. And what discrete means is this is your analog signal. Most of you are aware of your sinusoidal signal, right? And cosine signal, of course. These signals, as we see it, they are analog signal. And while these are the digital signal, because we digitize it. See, these are various steps we are using, and we are using only these values. Only these values, not all values, only certain values which approximately portrays this digital signal. So actually we are getting some discrete values. Those values which are discrete means different and precise. Those values, if they are taken, and these values are we are concerned with, these are called digital values, discrete values, and then this signal is automatically known as digital signal. So what are the advantages of using digital? Now the era is of digital values and everything is digital now, because the electronic circuits are quite cheap. First is the cheapness of the electronic circuit. Then you can easily calibrate and adjust these signals and the instruments which are associated with it. Then resistance to noise. This is also very important, because noise is always there. You cannot get rid of noise. Whichever electronic circuit, whichever way you, even while I'm speaking, this video might have some sound or noise beyond. Maybe you can hear it or hear it, or may not be. But there are some noises everywhere. You have clearer picture and sound. These are the benefits of using digital. Now, as we have known about digital, because we are talking about discrete values, then digital electronics starts with some number system. When you talk about 1, 2, 3, 4, these are called decimal system. Once you talk about 1, 0, 1, 0, these are called binary system. Some say some octal system, hexadecimal system. So there are variety of number systems available to calculate things, to represent things, to compute things. So we will be starting this binary system. So discrete elements of information are represented with bits which are called as binary codes. Discrete elements, we have talked about digital. Now discrete elements are there because discrete values are there. How we are going to represent it? We are going to represent it by or while using binary codes. For example, 9, you are aware of 9, 15 number you are very well aware of. These numbers are actually decimal numbers. The number which you have learned in your childhood, they are actually, in computer science we know it as decimal numbers. And once I write this number only in the form of 1, 0, means combination of ones and zeros, we call it as binary codes. Why we are writing this as sub 10? This is subscript 10, means this 09 is in decimal, while this 1001 is in binary. So there will be in later stages we are going to see the conversion between these various number systems also. So let me ask you a question. Why are commercial products made with digital circuits as opposed to analog? We have seen the advantages, but most digital devices, They are programmable. Means by just varying or changing the program in the device, the same underlying hardware can be used for various variety of different applications. This is the beauty of using or employing digital devices. Now coming to decimal code again, let me review it for you. We are reviewing the decimal numbers as I mentioned earlier, that the base of these numbers decimal is 10. The base or the radix is 10. What do we mean base or radix? We start from 0, we end with 9. Again, any number you take out, this will be a combination of 0, 1 to 9. There will be values from 0 to 9, because if I write some 9, 3, 2, okay, I write some number. This 9 and 3 and 2, these numbers lies between 0 to 9 only. So radix is 10. See, if you compute this number 0, 1, 2 on your fingers, it will be exactly 10. And for numbers which are less than 9, we add some significant bits or digits in position to the left. For example, 1, 9. 9 is okay. 1, 9, we say it is another decimal number, and each position carries a weight. How does it carry a weight? Say for 19, because this is how we represent it mathematically. This is the decimal point, because the number can be decimal 932.62. This can be a number. But how do I represent this 932? This is actually 900 plus 30 plus 2. So what exactly I am doing is I am multiplying 2 with 1. 10 to the power 0 is 1 only. Then I am multiplying 30 by 10 to the power 1, that is 10 to the power 1, that is 10. And I am multiplying 900 by 10 to the power 2, that is 100. I am multiplying it by 100. Right? And I am now trying to add this. What I am getting is 932. This 932 can be represented in this form. So decimal number can be represented in this form, and this is the left side of the decimal value. But if we want to compute the right hand side of the values which are on the right hand side of the decimal point, then the same discussion will go, but the power will be like this. 10 to the power minus 1 means I am multiplying 6 here, 6 into 10 to the power minus 1, then 2 into 10 to the power minus 2, and now I'm again adding 932 with this 0.62, employing this scenario, and these are MSDs. MSDs means the most significant digit. In 932.62 we have 9 as the most significant digit, while the value in layman terms, the rightmost value, which is 2, this is the LSD, lowest significant value. So if this number has to be shown, now the example I have already given you, so now you can very well find out that how to compute this using or represent this using your decimal code. Okay, this is, I hope you got the idea. Now when we come to binary number system, we have just seen decimal system. The binary system, now the base is 2 here. Only 2 symbols are allowed, 0 or 1. How does this 0 and 1 came? You have seen your switch, you either switch it on or switch it off. So when you switch off, it is 0. When you switch on, it's 1. It's just like that. So these are called binary digits. We take BI from here, ITS say, by here from TS from here, and it becomes bits. This is a short form of bits, is actually short form of binary digit. For a number which is greater than 1, we add more significant digit in position which is to the left, that is say 0. Of course 0 is less than 1, but if I add 1 here, 1 0 is automatically going to be greater than 1. How to represent this binary number in the same terms? Because I said for decimal numbers the base is 10, so we are multiplying each and every number depending upon the position by 10 to the power 0, 10 to the power 1. In the same manner, what I am doing is I am trying to represent it with binary system. So the number is multiplied, any number which is represented in binary, I multiply it by to the power of 2's. means 2 to the power 0, 2 to the power 1 and 2 to the power 2. Let me give you an example now. This is a binary number. This is the decimal point. I'm now concerned about these values, right? I'll take it later. These values I'll take later. So 1 0 1 1 1. So I start with 1. The first value which I encounter just after this decimal value. So what is this? This decimal value is 1. So I multiply 1 into 2 to the power 0. Just after decimal I have 2 to the power 0. So what I'm doing is I'm taking this number and I'm multiplying it with the first radix number or the base number of this binary number system. So 1 into 2 to the power 0. Then again 1, I encounter 1. Same. So I multiply it by 2 to the power 1. Then the third one, again third is 1. So I multiply it by again 2 to the power 2. Then again I encounter a 0 now. So I multiply 0 by 2 to the power 3, this position. Now I have one more position and one more value, that is 1. So I multiply it by 2 to the power 4. And the same thing, what I'll be doing with these numbers after decimal is I multiply 0 by 2 to the power minus 1. See, I multiply 0 by 2 to the power minus 1. I multiply 1 by 2 to the power minus 2. And I just add them. So when we add them, this is the simplest number of 23.25, and I'm sure, not might, but I'm sure that you will be recalling that these numbers are nothing but your decimal number. So this is how you represent a binary number like this. Actually, representation is this only. This is the actual formal representation of binary number. Once you want to find the decimal equivalent, this is the procedure you have to adopt. Now, hopefully, this is an exercise for you. Try to pause this and find out the answer. In computer system, 2 to the power 10 is 1024. Okay, 2 to the power 10 is 1024 in the same sense. If I am going to buy a vegetable, I say that okay, give me 1 kg of this, 10 kg of this, 8 kg of this. So the kilogram is the measure of the weight. In the similar manner, in computer science, the measure same kilo, the measure in computer science is 2 to the power 10. And if you multiply 2 10 times, means 2 into 2 into 10 times, then it will be 1024. So 1024 is nothing but 1 kilo. Don't confuse it, because 1 kilo is 1000, but here we have 1024. For computation purpose, various computation purpose, we will use this 1024 as 1000 only, means the same way we use or we adopt that kilogram thing. But 1024, if you want to multiply 1024 also, there is no problem as such. 2 to the power 10 is again 1024 into 1024, that is 104856. I hope this is mega, and try to multiply this and you will get the various advancement of kilo, mega, etc. So what is the exact number of bytes in 16 gigabyte? 16 gigabyte, this is kilo, this is mega. So what will be, or what is the exact number of bytes in 16 gigabytes? It's very simple. This is 16. You multiply this giga, means you replace just this gigabyte 2 to the power 30. So the answer will be 16 into 2 to the power 30 bytes. These number of bytes will be present in means 16 gigabyte. This is so simple. Now, as I mentioned earlier, we have octal and hexadecimal number systems also. What do we mean by octal? Octal means 8. So the base is 8. We start from 0, we end at 7. We don't go to 8. Right? We don't go to 8. So in some interview it was asked that okay, I'm giving you 832 as the octal number, converted into hexadecimal. The student tried to convert it, but he couldn't. Because the interviewer know that if a person knows about octal, he knows that the number 832 which has been given is actually not octal, because 8 is lying there. 8 will not be there, 9 will not be there. it will start from 0 and will end with 7 only. These numbers 236.4, they are in between 0 to 7, including 0 and 7. This is a octal number. How we are going to convert it from this octal to your decimal? We have earlier converted the binary number into the decimal number. Now we want to change or convert every number into decimal, because decimal number which we are aware of, everyone knows about decimal number. We are very much confident, everyone is confident and comfortable with this decimal number. So we need to know how to convert it. How we are going to convert it? The simple thing is, we use 10 to the power 0 for decimal, we use 2 to the power 0 for this binary, and for octal you use 8 to the power 0 because the base is 8. So 6 into 8 to the power 0, 3 into 8 to the power 1, 2 into 8 to the power 2, add them, and after decimal multiply it by 8 to the power minus 1, add them. 158.5 is the octal conversion of 236.4. This was octal, so this is the decimal equivalent of this octal number 236.4. Now coming to hexadecimal number system, the base is 16 for hexadecimal number. Now this will be a question, how to represent these 16 numbers, because from 0 to 9 we have only 10 numbers. For that, what researchers have done, they have used A to F. See, from 0 to 9 it is okay. For 10 they used A, 11 B, 12 C, 13 D, 14 E and 15 F. Now 15 is from 0 to 15, the numbers are 16 because we are starting from 0. Now this is okay. Now we can represent some hexadecimal number also. Hexadecimal number is very important as far as computer science is concerned, because most of the things are computed in hexadecimal terms only. Internally they'll go as digital only, but for representation purpose and for higher computer science stuff, you must understand this hexadecimal. So if you encounter in computer science later this kind of number, you'll say, is this a number? Because I have alphabets also. This is actually alphanumeric, but this is possible because we are using hexadecimal number. How are we going to convert this into decimal? Because we are going to convert everything into decimal, we need to know that. The same steps, the same technology. What? Multiply A. What is the value of A? That is 10. So keep 10 here, multiply it with 16 to the power 0. For F, what was the number we represented? F is 15. So 15 into 6 to the power 1. 3 and 6 will be multiplied in the similar manner. And for D, this is 13. So multiply 13 by 16 to the power 4. From right to left we take, from A to D we go. In the similar manner, we from 0 means 16 to the power 0 to 16 to the power n, depending upon the number of candidates here which we want to convert it into your decimal equivalent. So D63FA, the decimal equivalent of this hexadecimal number is 877562. Now converting from decimal to binary. Till now we have converted binary, octal and your hexadecimal to decimal numbers. But now what the other way around aspect is that I want to convert decimal to binary. So I have some decimal number, say 110. What I am going to do is I will divide 110 by 2. Okay, I'll divide it by 2. Say if I get 2 5s are 10 and 2 5s are 10. Again I divide 2 and whichever remainder or not remainder is remaining, I am going to write it here. 2 I divided from 110. 110 divided by 2, the remainder is 0. Again I divided this 55 by 2, the remainder is 1, because this is 2 2s are 4, 2 7s are 14. Again I divided by 2, 2 1s are 2, 2 3s are 6. What is the remainder? Remainder is 1. Again I divide 2, 6 are 12. Remainder is what? remainder is 1. Now 2 3s are 6, remainder is 0. 2 1s are 2, 2 1s are 2, remainder is 1. So I want to represent 110 in some form, and these are the number which I received, or these are the binary numbers which I received. So I can represent it. First of all, I'll just go to this slide first, and I'll come back to this, because this is very important aspect. This is how we do it in class. What way is there? First, I take 0, multiply it by 2 to the power 0. Take 1, multiply it by 2 to the power 1, and take 1 and 2 to the power 2, and I convert it into corresponding decimal. This is a simple conversion. How to convert it to decimal values. Now I want to convert now decimal to binary, so we divide it. So if I want to represent this 110, what I'm going to do is I will write it as what? This 1 1. I'm taking this. I take 1, then 0, then 1, then again 1, and then 1 and 0. Right? So please notice that I took this one first, wrote it here, and then I take each and every binary value which I received here, or rather the remainders which I received. Now I will compute it from here only, not from this. This is only for the writing purpose. I will start from the last one, and likewise I'll take all these values and write here. But for computation, or for converting it to a decimal number, let me see. 0, this is 0, so 0 into 2 to the power 0, 1 into 2 to the power 1, that is 2, 1 into 2 to the power 4, that is 4, 1 into 2 to the power, this is 1, 2, this is to the 1, 2, 3 and 4, 2 to the power 4. See, so 2, 4, 8, no 16, but here I have 32, because 2 to the power 5 and 2 to the power 6 is 64. If you add these values, 2 plus 4 plus 8 plus 36, 32 plus 64, you'll get a 110. So this is a simple way how you convert your value which is given in decimally to binary by dividing. So this is again an example. One more example, 37. So divide this 37 by 2. What you get? You get some number, but you have this one as a remainder, because 2 18s are 36 and you get a remainder. Then again you get 18, divide 18 by 2, you get a remainder as 0, because 18 is divisible by 2. So this 0 value, right? Again divide this 9 by 2, you get some value, but the remainder is there because this is odd. You get a remainder. Again divided this 4 by 2, you get a remainder as 0. Divide 2 by again 2, you get a remainder as 0. The last one is 1. So once you write, this will be your most significant digit. So you will write in this manner. So 1 is here, 0 is here, 0 is here, 1 is here, 0 is here, and 1 is here. This is how you are going to write. This is the only complication here. And once these numbers are there, you can easily multiply this by 2 to the power 0, 2 to the power 1, 2 to the power 2, and find out the decimal equivalent. So converting from decimal to binary, I hope you understand. This is simple division. Just accumulate these remainders and write from the lowest to the highest. So I hope you will convert this. This is an exercise for you. And this is another scenario, that like if you have a number of because we have not catered the case of decimal value, but if you have a fraction, means you want to convert a decimal fraction to binary, what you are going to do? Same thing, what you have done in this case, you divided. In this case, you will multiply. So what you are going to do is you take this number, even if some values are here, you just ignore it. You just take this 0.8542. It may be any value here. Just concentrate on the value which is after the decimal value. So what are the values after decimal? 8542. 8542, multiply it by 2. Previously we were dividing it by 2, but here we are multiplying it by 2. Multiply it by 2, what you are going to get? You will get some value, because this is actually 1.70484 value. This multiplication will result in 1.7084. So you take this one, and now you take you actually keep this value after decimal only. So the value will be only 0.7084 that you are going to retain. This one will be your binary conversion value. This will be your most significant digit. Again, multiply 7084 this value, means this value with 2. If you are getting some value in front of or on the left hand side of your fraction, take it. Means you get 0.7084 into 2 is actually 1.4168. So I take 1, I leave 4.468 for the next multiplication. I again multiply it by 2, right? I again multiply by 2, and I go this way only. So ultimately these values I will receive, and this conversion 0.8542 conversion will be this. I'll write here, this will be the first value. So 110 will be the final value. But the question will be till which number, because this is unending. This is not going to stop. You can multiply each value. You will take the value before the fraction or the decimal as your binary value. Okay, but what will happen to the value which you have retained? You can multiply it again and again. For that you have to know that you will be told that give answer to 6 digits. So because the answer is to 6 digit, we took only 6 multiplication. This is your final answer. If you want to convert a decimal value to octal, this is again very simple. Decimal to octal, decimal to binary, decimal to hexadecimal. What you have to do is decimal to binary you divide it by 2. Decimal to octal you divide it by 8. Very simple. Take the values. For instance, we take an example 1122. So 1122 you divide it by 8. You will get as some value 140 plus some decimal value. The value will be actually 140.25. What I will take from here is that there is a value in each and every division. For example, you have this 140, you divide it by 8. So when you divide 112 by 8, it will be 8 into 140 is 1120. The 2 will be remainder. So you take the remainder as 2. You divide 140 by 8, it will be 8 into 17, that is 136. The remainder will be 4. So 4 will be the remainder. In the similar manner, these values will be divided by 8, and these remainders will be taken. And these remainders, the last one will be more significant. The first one is the least significant. So how I'm going to write it is 2142, this way, 2142. So this is simple division. You just accumulate or collect those remainders, and finally you are done with the octal conversion. Okay, so this is how you can represent these values. Decimal is from 0 up to some 15, but decimal is only up to this value, and hexadecimal is 0 to F. Because why I have written 10 to 15? Because I just want to represent A with 10, B with 11, etc. But in decimal, 0 to 9 will suffice. Binary numbers are like this. 0000 is actually 0. 0001 is 1, because you have seen how to convert it. 2 to the power 0, 2 to the power 1. You multiply the rightmost value with 2 to the power 0, then 2 to the power 1, then 2 to the power 2 to the power 3, and likewise. And you will get the this decimal equivalent. It is so easy. So you convert it, you will get it as 1. And as the course will go along, as you will do some exercises, this you will learn by heart, because once this number will come to you, you will surely be knowing, okay, this is 14 without even computing. Octal number 0 to 7, right? So this is an aspect of conversion using table from binary octal hexadecimal. We really know that 2 to the power 3 is 8, 2 to the power 4 is 16. Okay, so how this is a very simple method. If you have a binary number, what you're going to do is, I wish to convert a binary number into octal number, and I wish to convert a binary number into a hexadecimal number. So how simple it is, because we know 2 to the power 3 is 8. So I combine only 3. I make combinations of 3 values, only 3, 3, 3. See, these 3 values. And for hexadecimal, the combination will be of 4 values, means 4 binary terms. This combination is 4. These are 4 values and these are 3 values. Now this 0, 0, 0 in binary, it is 0. In 0, 1, 1, it is actually 3. If you convert 0, 1, 1 in decimal, it will be 3. 0, 1, 1 in decimal, convert it into decimal, you know it very well, it is 1. So 1. And you know the values which are on the left hand side of your decimal value will be like that only. 1, 0, 0, you know it is 4. 0, 1, 1, 1, it is 7, and 0, 1, 0 is 2. In the similar fashion, the way we combined only 3 values and converted a binary value into an octal, in the similar fashion, for converting this hexadecimal to, for hexadecimal conversion, means from binary to hexadecimal, I take 4 combinations. So 0, 1, 0, 0 is 4. I'm interested in this F. 1, 1, 1, 1. You know this 1, 1, 1 is what? F. So this is by table. 1, 1, 1.